Okay, what I want to go over with you now is the basic concept behind integrated rate laws. Okay, so I'm going to do the concepts behind them. Some of you guys who have had calculus, see some calculus up here. If you have not had calculus, that's okay. You don't need to know it for this. But for those who have had it, I want them to see it. Okay. So let's take a more basic chemical reaction. Instead of A plus B going to the product, let's just choose A going to the product. The rate of the reaction from before is minus delta A over delta T. And the rate of the reaction is also R equals K A to some power. What we want to do is relate the concentration over time. Okay, so we want to know if we start the concentration at 1 molarity and then I run it for 100 minutes, what will the concentration be then? And we want an equation for that. Well, if this is equal to reaction rate and this is equal to reaction rate, two things equal to the same thing are equal to each other. Law of excluded middle. So I could say minus delta A over delta T is equal to K A to the M. If I bring the A down underneath here and the delta T across and I move the minus sign across and I let this delta, instead of it being a large time difference, and large concentration difference, I let the difference go to infinitesimally small. Then I get dA over the concentration of A to the M is equal to minus K dt. And if you ignore these integration signs, you could see that you can take this and turn it into this. Just bring this piece down under here, bring the delta T up over here, move the minus sign, you can do that, and I get this. Now, at my starting concentration is when I have, the experiment has no time elapsed, that's the starting time. After a certain period of time, I will have a particular concentration at that time. If I use the rules of calculus, I can get 3 different equations out of this that will tell me the concentration of chemical A at a specific point in time. So let me calculate it. And it matters what the value of M is, because remember, M could be 0, 1, or 2. Now, without going through the math, if M is 0, then the concentrate, if I do this calculus stuff, out comes this. Those of you that have not had calculus can kind of skip that piece. And so then you would go from here down to these 3 equations. If M happens to be 0, then the concentration at any point in time is equal to minus K times time, K is a rate constant, plus the initial concentration. If M is equal to 1, then the natural log of the concentration at any point in time is equal to minus K, the rate constant, times the time, plus the natural log of the starting concentration. Where did that come from? Calculus magic. Okay? If M is equal to 2, then I end up with 1 over the concentration at a point in time is equal to positive KT plus 1 over the starting concentration. Okay? So if you're given a starting concentration and the value of the rate constant, you could calculate the ending concentration after a specific period of time. 100 minutes, 500 seconds, whatever. Okay? And we're going to learn how to do that later. One other thing I want you to know is for a first order M equals 1 reaction, very often, instead of using it in this form, we'll use it in this form. And I'll show you how to use both of these. Okay? So there's that. Now remember these equations, because I'm going to erase up here, and I want to show you something. If I ran an experiment where I had chemical A in a container, and it was turning into chemical P, and I plotted the concentration over time, here's my data points and my best fit line. If M is equal to 0, a graph of concentration versus time will give me a straight line. And the slope is equal to minus K. Not K, but minus K. Okay? So, if it happens to be a 0th order reaction, and I measured the concentration over time, you'll make a straight line going down. And that's because, I'll show you in a minute, but let me erase this. If it happened to be first order time, and I made a plot of the natural log of the concentration, T, P, I would get a straight line. Natural log, if M is equal to 1, I would get a straight line going down. And the slope, y2 minus y1, x2 minus x1 is equal to minus K. If it was second order, a plot of 1 over A versus time, we'll make a graph looking like that, going up, where the slope is equal to positive K. Right? Why does this fit a straight line while natural log of time, natural log of this versus time makes a straight line, and 1 over this makes a straight line? That's because the equation of a straight line, y equals mx plus b, that's the equation of a straight line. And if it's 0th order, remember I told you got minus kt plus, at plus a naught. That's the equation of a straight line. This is why k is your slope m, x is your time, and that's your intercept. If it's first order, natural log of a, t equals minus kt plus natural log of a naught. Y is natural log of a, minus k is m, t is x, and natural log of a naught is the intercept. And if it's second order, 1 over a naught is equal to positive kt plus 1 over, not a naught, 1 over at, 1 over a naught, where this would be y, 1 over time, this is x, k is the slope, right, fits the slope, and 1 over at, here's the intercept, that right there is 1 over a naught. This intercept right here is the natural log of a naught, right, intercept, and this right here is just a naught, the intercept. So if I were to plot, if it's 0th order and I plot A versus time, I'll get a straight line. If it's 0th order and I try and plot natural log of A over time, I won't get a straight line, I'll get a curvy line because it doesn't fit. If it's 0th order, it won't fit a first order graph. And so on. Okay? So I need you guys to understand that. Where did these come from? The previous whiteboard that I just erased. When I integrated and I do the math magic, these equations pop out. These equations are all fit the equation of a straight line. And so if I were to plot this, what kind of graph would I plot? I would plot AT versus time. Here, plot natural log of AT versus time. And I plot 1 over AT versus time. So I want you guys to understand those concepts, and then in the next installment, I'll go ahead and solve some problems for you. But I wanted you guys to know that and have been taught that, okay? All right, I'll see you guys next time.